You can see my long name. I go by Muthu, but my full name is Venkataraman Muthuramalingam. Last summer, we actually embarked on our capstone project through our Harvard data science program. We actually took as a continuation of work our previous cohorts have done with Lyme disease and understanding the Lyme disease prevalence across the United States. And we sort of continued their work to focus more on early warning system. Our previous cohorts largely focused on Lyme disease prevalence and how to understand the prevalence itself and the spread, but we focused on continuing their work, but largely to develop a system that can provide early warning of Lyme disease prevalence. As you know, this is one of the disease that is not so very well tracked in today's world, and we'll probably talk about it more in my upcoming slides. But that was our main focus, and we leveraged Twitter data to build this live streaming system to provide early warning. Just first, a quick set of acknowledgements. We worked closely with Professor Nasri and our previous cohorts and professors from Harvard, as well as a bunch of distinguished previous cohorts, individuals that we were able to get their time to kind of understand their previous work, but also share our experience throughout our project journey that we started last summer. We actually concluded our capstone work just this past December. And the work that you're going to see here is that finished product. Like I said, we were the three individuals, June, Jack, and myself. Today, for the presentation, I'll cover these 5 agenda items. We'll go through quickly the background objectives, how we went about doing data collection, labeling, and also what we observed from the data that was available from Twitter, and finally, taking the developed model and enabling it for live stream and live monitoring of Lyme disease prevalence through Twitter data. And then we'll also finally cover some of the things that we feel there's a lot more work to be done here, but we feel that we benefited out of this experience, as well as what next can be done. Lyme disease is obviously a very a chronic disease that people suffer if they get it, and it can ultimately lead to death as well. But it is a very chronic disease, and that's just the nature of it. Most importantly, the surveillance data that is available today from public authorities, those are really 2 years plus old data. Whether it's US or Canada, there's very little live data available for monitoring the prevalence and trying to understand and see how quickly we can react if there is indeed an outbreak of Lyme disease. For that matter, any disease, but we focused on Lyme disease and Lyme disease related data from Twitter. The problem statement is basically not having live data available to understand, and it requires work to get live data, or rather current data, and the work that goes behind getting public data typically starts with somebody individuals having health issues. They go through the treatment process. The actual surveillance data is collected through hospitals and testing labs that gets aggregated and published for CDC to understand the prevalence in the case of United States, and same goes in Canada and other countries. So there is time involved in collecting this data, and that's why it is 2+ years old data that exists today, and that's the challenge that we deal with. So our surveillance that we focused on, we said, hey, that's the core issue. We need to, figure out how we can provide supplemental data, not necessarily, provide more, authoritative data. The authoritative data still comes through labs, and labs produce results that get segregated, and the public authorities publish and use them. But we said we can use social media data to, kind of generally predict, do an early warning forecast. If we truly see somebody, tweeting about their Lyme disease, positive Lyme disease situations, we can glean that data, their locations, and provide live information, up to the minute current information that is still not as validated as the data that can be available from labs. It is still somebody voluntarily sharing that information and sharing. And in fact, as we worked through our project last year, we honestly observed and felt really sad for some of the tweets that we saw. That people were truly talking about their sufferings. So and we took that data to kind of understand the prevalence and produce real-time dashboards. So that's what we did. And the approach we took, obviously we went through first initially collecting about 6,000 tweets and manually classified them for our model training purpose, and split them into obviously training and test data sets to further build our model. When we looked at the data itself, obviously we had to curate the data for model development purpose. We focused on converting some of the common words and occurrences into our own customized tokens, so that and we added our own customized tokens to the data set, so that we can further use for our model development and training purpose. The data split, as you can see here, when we classified it as not related. So obviously tweets, when you search for Lyme disease tweets, you'd see tweets that are very general, article related tweets, or people are truly talking about their positive case experiences, or tweets that are Lyme disease related, but not but they are not positive cases. So we were able to glean them. Zeros are easy. Zeros meaning they're not related. One is it's basically Lyme disease related tweets, but they are not positive cases. But then the true positive cases, which is number 2 here, that's our labeling that we use, 0, 1, and 2. Which is about 10% of the data that we collected were truly positive cases. So it's not there is class imbalance here, but we were able to work through this, the class imbalance that we dealt with. And some of the further exploratory data analysis revealed tweets are better used for us. None of the tweets exceeded more than 100, about roughly in that 100 to less than 150, 160 tokens for us to work with, which is very good for, especially when we are building language models and doing the language or rather tweet models or bird models. And we have to do our classification. It's much easier to work with smaller messages as opposed to lengthier text. So that's what we observed. Some of the common words that we observed through our exploratory data analysis, you can see here, chronic is more prevalent, Lyme disease, tick-borne diseases, symptoms. So there's some of these common words we were able to glean. There's about 50 common words that we saw out of this 6,000 tweets. And even these are very commonly occurring words that we observed. Even as we developed our model and enabled it for live stream, we were able to kind of relate to what we saw in our training and test data sets with real life tweets. So that's in a nutshell. And then the approach, again, is kind of a little bit elaborative flow here that kind of outlines how we went about working, collecting our tweets, go through the classifications, develop the bird tweet model, and then implement it in an execution environment. For our project work, we were offered Azure Cloud, and we actually ran the model in a live environment, and actually had live dashboards available. Unfortunately, as we concluded our project last December, that Azure instance and the access that we had, we no longer have. So I won't be able to demo the live dashboards today, although I am actually reconstructing all the implementation work that we did over the last few weeks. I plan to actually bring it back to live on my own personal instance, because it is invaluable work, and I feel there is value that the future cohorts if they want to continue working. And I would like to continue to show and promote the idea of this live data capture and live monitoring is going to be invaluable. So anyway, this is the approach we took. We were able to implement the execution model in a runtime environment and actually stream live data, classify them, and create visuals out of our classification. So we did all that as part of our project implementation. I have actually all those dashboard screenshots available. I'm going to kind of quickly walk through them as well. Now, specifically to focus on the model itself, the model training, we went through several iterations. We were able to achieve optimal performance, slightly better than our previous cohorts. That's largely due to us working with better tokenization and better classification, and we got nearly up to 96% accuracy. This is in relation to still not having a good strong class balance, and then we worked with fairly high F1 precision and recall scores for our bird tweet model. These are some iterations and the scoring percent for various learning rate, batch, and layers output. The chart that you see here. So I want to kind of skip right past through this and dive into, unless there is anything specific that stands out that I wanted to talk. No, nothing specific. I mean, it's kind of elaborates further. Obviously, we will share this deck for reference, and we actually have all the model development code and our data sets in a repo. Our GitHub repo is, I don't think we've published it yet, but we're going to publish it and make it available for general open source community use. But all of our work is actually organized in our GitHub repo. So now finally the visuals themselves, and unfortunately I don't have a live demo to show. It'll be really cool to show the live demo, but the visuals of the tweets, we represented them in a number of different dashboard widgets. One of the widgets that you see here is the map visualization, which is essential when a tweet originates. If we can identify the geographic location of those classified tweets, we can actually place them, geo place them, and that's exactly what we have done here. And we can actually zoom in this map, go into a specific state, city, location. And of course, while we talk about CDC data, we focused on English tweets, and if English tweets we could classify across the world. And that's what is represented here. We were a little biased in working with only English tweets. There is opportunity to work with other language tweets, especially French, German, Italy, or Italian. There is opportunity for us to build language translation and then do the bird tweet model execution to classify those other language tweets as well, and get more meaningful representation of Lyme disease prevalence geographically. So that this is one of the chart. Again, here we can look at time-bound data. We can look at the last 1 week, last 6 months, however longer we have data we have classified. If we persist and keep it, we can actually filter them. And this is very visual, and we can zoom in and go to, and we can actually go to the actual tweet messages that classified a particular tweet as positive prevalence. We can actually look at the tweet message, and we have those capabilities within this tool. Elasticsearch is the tool that we use for visualization, and actually it allows us to not only zoom in to see the prevalence, actually see the actual tweet if we wanted to. So that's the benefit we get out of the tool. There are other visuals like looking at the counts by duration, and we can actually, if we filter one widget, all the other widgets will collapse to that duration or that location or those those tweet words that we want to kind of exclusively filter and see. Visually representing them, we were able to actually collapse all of our widgets to condense the data view to what we want to see. So that's the power of not only getting this real-time data, but also being able to do more zoomed in view. So that's this is another view of looking at a bar chart, or looking at some of the prevalent words and their occurrences throughout a particular day or hour. We can filter, Lyme disease, chronic. So we can actually filter, and we can call out words that we want to see as well. And that's the power of this visual tool. And then we've created a word cloud, top 10 values, top 10 words, and these are customizable charts, customizable views, and these can be done once once those tweets are classified. We have the power to work with the data and create widgets that we want. So that's exactly what we were able to achieve with this tool and as part of our project objectives. So some of these visuals I just want to kind of show. And this last chart is basically, it's always fun to see cool visuals, but it is not practical for especially public authorities to sit in front of the computer every day and look at those cool visuals all the time. It's important that on a particular day when the prevalence exceeds a specific threshold, let's say, geographically we want to look at a specific state or a city, and not only that, do we want to look at, hey, on a given day, if a threshold violation happens, I need to get alerted on it. So that's when I want these charts and visualizations become more meaningful for me, because I can now, because I have an alert, I can actually come here and take a look at what's happening. So that we were able to create a mini upper bound, lower bound, manual threshold, and generate alerts off of that. But this tool is very powerful. We can do anomaly detection on a specific pattern, tweet pattern, and actually even any anomaly violations occurring can also result in an alert. And that's when the alert can go to public authorities, and they can actually come here and make use of these visuals. So that's something we further invested our time on as part of our project work. So that's the high-level overview I want to kind of quickly share, and some of the lessons learned are bulleted here. We looked at many places to see if there are any such live nowcasting dashboards are available, and we couldn't find anywhere. So we like to claim that this is the first nowcasting dashboard for Lyme disease, but this need not be just for Lyme. There is work that can be done to expand for other diseases, and like I mentioned, for other languages. We can look at as well and try to classify and build live streaming dashboards and help public authorities to take advantage of such capabilities and be proactive and not and get in front of any specific outbreaks, and that may or may not happen, or that may be waiting to happen. Like I mentioned, the future work is to continue to expand beyond English language. One of the other challenges, we obviously for our project we focused on Twitter data. Even tweets had limitations. Not all tweets had geographic locations. So even the ones that we were able to exclusively classify, if we couldn't get the geographic location, we can't place them on our geographic map. So we don't know where those tweets are coming from. So that's the other drawback. But then, we take what we get. That's how we went by. And there may be other avenues we can explore for more authoritative information. Professor Nasri actually had broader scope for us. Even as we embarked on this journey back in early last summer, including looking at other social media like Reddit. But we narrowed our focus on Twitter, but there is obviously opportunities to expand beyond tweets and look at other social media for more authoritative information, or more information that actually smells like some problem is brewing. So let me pause. That's all I want to kind of quickly cover today, and ready to take any questions.
Thank you very much. Maybe I will start with a very simple question, because I'm extremely skeptical with this kind of study. But what if, just imagine, like, you got Justin Bieber in 5 days in Hawaii, you got a friend in Florida who got Lyme disease, so he's going to tweet from Hawaii, and he will get a lot of retweets. So basically, you will say that you got an outbreak of Lyme disease in Hawaii, right?
Yeah. Yeah, sorry, there was too much echo and I couldn't hear the entire question. Can somebody close the microphone? Just kind of restate the question. I apologize. I know I heard Hawaii or prevalence in.
That's okay. So you got Justin Bieber, who's
Oh yeah,
100 million followers, right? So he's in Hawaii. You got the location, so you know that the location.
right. Oh, I got you. Yes. Yep.
In the US, we got Lyme disease. He
Yep.
tweets about that in Hawaii. He will get a lot of retweets. So you will say, okay, there's a lot of activity around this this tweet.
Yeah.
So I mean, I'm not sure what
retweets. Those are, the question is around retweets, right? So we did ignore retweets because we didn't want to, because one tweet is about one person. People are retweeting doesn't mean there is hundreds of thousands of tweets, doesn't mean it's hundreds of thousands. Yeah. So we did avoid retweets, reposts. We in fact, in our data, we could clearly see it's all unique occurrences of tweets, not exactly.
Someone saying, "Oh, I'm very sorry for you, Justin," and is maybe in,
exactly. Somebody sympathizing doesn't mean. Yeah, sorry to speak over you. Yeah, that's very valid. We did ignore retweets.
Okay, but I'm excluding retweets. I'm just saying someone says posting an answer, and you will get a lot like, Justin, I love you, I'm very sad for you. That guy is in Florida. So you will get someone in Florida talking about Lyme disease, but there's absolutely nothing in Florida about Lyme disease.
Yeah, you know what? That's a great point. You're right. If it is a tweet response, we don't look at that either. So tweet responses, we don't look at that. Retweets, we don't look at that. But new tweets like that, it's hard to stop. I totally agree with you. We in fact, we looked at, again, those tweets, if they actually have, so some of those tweets feel sorry for you, etc. Our models are not trained on them. So you won't see those because the model is just as good as looking at those tokens, right? Tokens is what matters to the model performance. So if there are misleading tokens in the tweet, you are right. There is the chance of misclassifying a tweet as a disease when it is really not a disease. What we observe, see, one thing we observed is every day, as we were when we finished developing our model and we enabled our data collection, live data collection, every day we would just look at it. Hey, how good is our model performing? We would actually go into the data, query it for how good it's performing, because you got to remember, what we are collecting is only those tweets that we care about. So if there are 100,000 tweets a day, we would only have about probably 300 tweets that really matter to us. And that's what we will be looking at. So it wasn't as laborious for us to kind of take a quick peek every day. Our model performed very well to only tweets, to a large extent, only tweets that people were truly talking about their sufferings and what is happening to them, and how they've been diagnosed. And some of them are chronic. So it's not like it's happening right now. They're talking about chronic disease that they had been suffering for the past 10 years. So, but then it's happening. People are suffering. So we did classify those chronic diseases or chronic instances as a prevalence, because it is still happening to them. So we did see those tweets, but we should not be naive. To your point, I think you have a very valid point that we need to kind of continually monitor our model performance to see how effective it is to prevent misclassifications. And occasionally we may require even retraining our model. And for the duration of our project, we didn't face that, but for the life of such a solution, we'll have to think about those challenges.
Great, perfect. Thanks a lot.